When solving chemical equilibrium problems, it's important to know just how that chemical reaction is going to shift as it reaches equilibrium. There are two ways that we have to describe the shift that takes place as equilibrium is reached. First, we need to know what direction is it going to go. Is the reaction going to make more products, that is, shift right, or is the reaction going to convert products into reactants, which is to say, shift left? The other thing that we need to know is the degree to which this shift takes place as equilibrium is reached. If the reaction shifts strongly, large amounts of product may form if it shifts to the right, or large amounts of reactants may form if it shifts to the left. On the other hand, slight shifts are possible, or weak shifts. That is to say that only small changes in product and reactant amounts take place. To demonstrate this, let's look at an example. Here we have H2S in equilibrium with hydrogen gas and S2 gas. The equilibrium constant for this reaction, K sub C, is known to be 1.67 times 10 to the minus 7th. What we notice right off the bat is that this value of K sub C is a very small number. Recall that small equilibrium constants favor reactant formation, which is to say when equilibrium is finally reached, we should have mostly reactants present with only slight amounts of products. This is an equilibrium that favors the reactants. Let's see how this might work given some initial conditions. Here I have an initial concentration of H2S equal to 0.500 molar. The red bar there demonstrates in a bar graph how much H2S that I actually have. Now that's the reactant. On the product side, we initially begin with no H2 and no S2, so there are no products present initially. However, equilibrium does require non-zero products and reactants in all places. And so here, in this case, we can see that the equilibrium must shift in the direction of the two places we have where zeros are found. So in order for this equilibrium to be reached, it must shift to the right to create an amount of H2 and an amount of S2 that is not zero. It'll be a very small shift, however, because the equilibrium constant still favors reactants. And so once equilibrium has been reached, everything, or most everything, should be on the reactant side with only small amounts of product, just enough to satisfy the law of mass action and determine an equilibrium constant. In subsequent lessons, we'll look at how one actually determines the equilibrium levels, but let's just skip ahead to the answers. Once equilibrium has been reached, we find that 0.499 molar, hardly a change at all, of the H2S is there at equilibrium. Only a small amount of the H2S has been converted into products. The product amount, the hydrogen gas amount at equilibrium is 4.37 times 10 to the minus 3rd molar. A very small amount of H2 is present at equilibrium, and an even smaller amount of S2 is present at equilibrium, 2.18 times 10 to the minus 3. Again, this is consistent with the idea that this is a reaction that favors reactants. That equilibrium constant being so small tells us that in the end, once equilibrium has been reached, we should have mostly reactants present. Another way to look at this, or to say this, is to say that the reaction shifts slightly to the right, just enough to create product amounts that satisfy the law of mass action, and this chemical reaction is now at equilibrium. Let's look at another example of how a chemical reaction can shift as it attains chemical equilibrium. Along the way, we'll determine which direction the reaction is going to shift and to what degree the reaction is going to shift, whether it's a strong shift involving large changes in product and reactant amounts or a very weak shift involving smaller changes. We'll look at an example that we've already seen before, H2S in equilibrium with its product amounts H2 and S2, and recall that the equilibrium constant for this reaction is a very small number. In fact, this is a small number that tells us right away that this is a reaction that will favor reactants. In the end, we expect to see a lot of reactants. However, unlike the previous example, we start out with initial amounts, in this case, 0.500 molar H2S. This is just like the previous example. However, what makes this one different is that we're also starting out with a significant and equal amount of the one product H2. 0.500 molar of H2 is also present initially. Initially, there is no S2 gas present. Now, as we know, equilibrium requires non-zero product and reactant. And in this case, we have non-zero H2S and we have non-zero H2. However, the equilibrium will shift in the direction of zeros, and in this case, we do not have any of the S2 product. So this means that even though we have H2S and H2 present initially, the zero in this case dictates that the reaction must shift to the right. The reaction must shift in the direction of zeros because at equilibrium, you can't have any zeros in either product or reactant amounts. This is going to be a very slight shift, because we know the K sub C is very small and favors the reactants. However, something that sets this example apart from the previous example is that we already have pre-existing concentrations of one of the products. The H2 in this case starts out with 0.500 molar. This in effect gives the products a head start as equilibrium is reached. We already have one of the products present, and we know that we would like as much of the reactant present as possible. What this is telling us is that since initially there is significant H2 present, the shift that's required is going to be very, very small since we already have some of the H2 gas present. All right, so a very slight shift is ahead, and we'll skip ahead to the final equilibrium amounts. At equilibrium, having solved this problem, we determined that the amount of H2S present, and recall this is going to be a shift to the right now, so we expect some of this to be used, is very, very, very near the original amount. 0.4999996 molar is what we have present at equilibrium. A very, very slight drop in H2S concentration. And in fact, within the significant figures that we can report, this number would have to be rounded off to 0.500 molar. Yes, it did drop some, but within the significant figures that we can report, the amount is practically identical to the amount that we initially started with. Okay, so this shift to the right didn't change the H2S levels very much, and it did increase the hydrogen gas concentration a small amount. Again, 0.500000334 molar is the new concentration of H2S. However, if we report that within the significant figures that we can actually report, this winds up being rounded off to 0.500 molar again. So a slight shift, but nothing that we can report within the significant figures that we have in this problem. However, there was no S2 present to begin with, and this is the motivation for the shift to the right. And upon solving for the S2 concentration, we find a very, very small amount, 1.67 times 10 to the minus 7th molar. This is 4 orders of magnitude less a S2 than was produced in the previous example. So a very small amount of S2 is actually present, just enough such that when we put these equilibrium values into the law of mass action, we would get a value of the equilibrium constant, which again is a very small number. So there you have it. In this case, this reaction, like the previous example, does shift to the right, but unlike the previous example, given that it has H2 that's been given a head start, shifts very, very slightly to the right, just enough to produce a small amount of S2 that satisfies the equilibrium conditions. We're going to continue the exploration of chemical equilibria and the direction the chemical reaction shifts with a different example. This example involves nitrogen gas and hydrogen gas as they're in equilibrium with the product NH3, ammonia. Unlike previous examples, this equilibrium constant is actually a very large number, 3.7 times 10 to the 8th. Such a large equilibrium constant, we say, favors the products. Okay. This is telling me that once equilibrium is reached, we should have a lot of product present. An initial condition begins with absolutely no N2 present and no H2 present. There are no reactants present initially. However, there is an initial concentration of the product, NH3, and it is at 0.500 molar. As we've seen before, equilibrium requires non-zero product and reactant amounts. In this case, the equilibrium must shift in the direction of the zeros, and the two zeros are both reactants. Thus, the reaction is going to shift to the left. It has to. because at equilibrium we have to have non-zero amounts. But keep in mind that this is an equilibrium that favors the products, and so we're beginning with products we don't expect much of a change. Skipping ahead to the solution, the equilibrium values, we find that a small amount of the N2 gas is present at equilibrium, 2.23 times 10 to the minus 3 molar. A small amount of the H2 is present at equilibrium, 6.70 times 10 to the minus 3 molar. These were produced at the expense of the product, NH3, as it was converted back into these small levels of reactants. Its value has dropped down to 0.498 molar, a very small change, very close to the 0.500 we began with, but some of it was sacrificed in order to produce the reactants now that are there as we've reached equilibrium. This is a reaction that has shifted slightly to the left, consistent now with the equilibrium constant that at equilibrium we should have mostly or a lot of products present and only small amounts of reactants that are present. Let's continue to explore how chemical reactions shift as they attain equilibrium with a familiar example. This, again, nitrogen gas and hydrogen gas combining to make an equilibrium NH3. The equilibrium constant, K sub C, is a very large number. Again, this tells us that this is a reaction that favors the formation of products. In other words, at the end, once equilibrium is reached, we expect to see a lot of products around. Now, initial conditions. Like the previous example, we have no nitrogen gas present. But unlike the previous example, we have a significant amount of the reactant, H2, present. Additionally, we have 0.500 molar NH3 present. Now, like all equilibria, we cannot have zero amounts. 0 molar for nitrogen gas is not allowed in an equilibrium setting. And so the equilibrium must shift in the direction of this zero, which is to say that it has to shift to the left. We need to gauge in our minds, though, just how much this shift is going to be. Now, there are two factors to consider. First off is that the equilibrium constant is going to want to see a lot of products present and as little reactant as present as possible. But the second thing to consider is that we already have a pre-existing amount of reactant. The hydrogen gas is already there in a significant amount, which gives this shift to the left a head start. We won't have to shift the reaction as much to the left to generate reactants because we already have one of the reactants present in a significant amount. So by way of both arguments, this shift to the left, keep the products, and oh, by the way, you have a lot of reactant present to begin with, at least the hydrogen gas. The shift to the left is going to be a very small shift because very little N2 will be required to reach equilibrium with such a large amount of H2 present initially. Skipping ahead to the answers now, the amount of N2 that's present at equilibrium is a very small number, 5.40 times 10 to the minus 9th molar. Hardly any at all, just enough to satisfy the equilibrium requirement that we have no zeros present. The amount of additional H2 that's generated isn't even enough to show up in the significant figures we can present in this problem, and so I've rounded to 0.500 molar. Likewise, the amount of shift to the left that removes material from the product side isn't reportable either within the significant figures of the problem. One can then say that this is a reaction that shifts to the left, but in comparison to the previous example, it shifts very, very, very little to the left as we have this pre-existing concentration of H2 making the shift left much slighter than what we had seen previously. Up until this point in time, we've looked at chemical equilibria and shifts that were very small, slight shifts, small increases to either products or reactants that are consistent with the size of the equilibrium constant. Now we're going to switch things up a little bit and look at a different type of chemical shift. A familiar chemical reaction, H2S, in equilibrium with the products H2 and S2, has an equilibrium constant that's very small. And as you should recall, small equilibrium constants, why they favor the reactants. Thus, at the end, once we've determined equilibrium amounts, we should have a lot of reactants present. In this case, however, initially, we're going to look at a slightly different setup. Initially, we have no reactants present. However, the product amounts are significant. We have 0.500 molar H2 and 0.250 molar S2. Okay, so in this case, the rules still apply. Equilibrium requires non-zero product and reactant amounts, and the equilibrium still must shift in the direction of zeros, which we have here. The reactant H2S amount, reactant amount is 0, and so the reaction is going to shift to the left. However, this is going to be a large shift. Remember, we've got an equilibrium constant that's telling us that this is an equilibrium that favors reactants, and we initially have no reactants. So this is going to mean a significant and large change in the reactant concentration. The H2S concentration may begin at 0 molar, but it's going to end with some very large amount present. And where are those amounts going to come from? They're going to come from the product side. This reaction is going to shift to the left in a very big way, as we need lots of reactants present once equilibrium has been achieved. Skipping ahead to the solution, the equilibrium levels reflect this very large shift to the left. The amount of H2S present once equilibrium has been achieved is 0.499 molar, quite a big change from the 0 it began with. And the amount of H2 present, as this is an equilibrium that favors reactants, not products, has dropped down to a very low level from its initial 0.5 molar to 4.37 times 10 to the minus 3 molar. Similarly, the S2 levels have also dropped to very small numbers from 0.250 molar to 2.18 times 10 to the minus 3 molar. A very large shift to the left, creating reactants at the expense of the products. Now, some things to note about problems like this. It is a reaction that shifts strongly to the left. Whenever we can predict a strong shift, then it's time for a problem-solving approach known as the material shift. A material shift is a procedure that's performed before the equilibrium problem is solved, and this will be the topic of the next discussion.